When we're working with redox reactions, we often work with only half of the reaction at a time. This is our first and most common way of balancing redox reactions. We separate them into half reactions and then we balance them separately and then put them together to make a complete balanced equation. So we're going to look at some examples of how this might work. So the reason why balancing half reactions is necessary is that rather than seeing a reaction like this, where we see all the chemical species, including all of the ions, all of the counter ions, for example. So in this case, it's very easy to see what needs to be balanced. We can see those two nitrates, and so we know that we need to balance with two silvers on both sides. So if we have this form of a chemical reaction, the way we did when we were balancing chemical reactions earlier in the term, then we can just balance them. But that's not usually how we see it. Instead, we're going to see something like this. And so if we're just looking at the atoms, the way we did back in our earliest part of our balancing, then we see, oh, we've got one silver here and one silver, that balances. One copper, okay. Not a big deal, right? We can't see these anions to help us figure out how we need to balance it. So instead, what we do is we separate into half reactions, and then we follow a series of steps to balance it. Now, we aren't going to need to go through the whole process here with this very simple equation. So we're going to look at this simple equation, and then we're going to look at a little bit more normal equation that we might expect to see, and see how all of those steps manifest, and then we'll practice it again. So when we separate these into half reactions, what we're doing is we're separating them into the reaction where oxidation takes place and where reduction takes place. So depending on what your reaction looks like, you might be able to immediately recognize what's going on in this chemical reaction, or you might just separate them by the elements, right? I can see here that my silver needs to be with silver and my copper needs to be with copper. So if I'm looking at oxidation, I'm losing electrons, that would be my copper. So that would be my oxidation half reaction. And then this would be my reduction half reaction. But it's actually less important to specifically label them as oxidation and reduction, and more important just to separate them based on, hey, we've got electrons and they're changing between these two sides. What we don't want to do is we don't want to mix up our chemical species. So we want to keep the element that is being oxidized separate from the element that is being reduced. Okay, so what we need to do in order to balance these is to look at the electrons. Since our elements are already balanced, we don't really have anything else going on. We need to balance the charge. And we talked about this a little bit in the previous video, that just like balancing atoms, we also need to balance charge. So we can see over here on this left-hand side of the copper reaction that the charge over here is 0, but the charge over here is +2. Now, the only way that we can balance the charge is by adding electrons. So we can make things more negative, but we can't make things more positive. So that means that in order to balance this copper, we need to add 2 electrons, because those are 2 negative charges, to balance out those 2 positive charges. And now over here on the right hand side, we have a total charge of 0 as well. All right, so over here in the silver, we have 0 charge over here on the right hand side and a +1 over here on the left hand side. So we need to add 1 electron to balance the charge over here on the left-hand side so that the left-hand side charge is also 0. Now, you won't always have a total charge of 0. It just really depends on what your reaction is like. The important part is just that they have the same charge on both sides. Okay, so when we look at these two equations now, you can see that one of these reactions has 2 electrons and one of them just has 1 electron. So we need to not only balance the charge in each individual reaction, but we need to balance the number of electrons between the two half reactions. So in order to do that, we multiply by a whole number. And so we can see if we have 2 electrons here and 1 electron here, we need to multiply this whole second reaction by 2. So we're going to update it, and I'll just write it down here. This becomes 2 electrons plus 2 silver ions. Oops, not plus. Makes 2 silver solid. And then the final step is going to be to add the half reactions back together. And so when we add the half reactions back together, the electrons must balance. If they don't balance or if they don't cancel out, then you haven't done it right. And so that's a good self-check. So if we add these two together, we're going to add everything on the reactants side. So that becomes copper solid plus 2 electrons plus 2 silver ions. And now everything on the products side, so that's copper 2 plus 2 electrons plus 2 silver. And so we can see now that these 2 electrons are canceling each other out, and that's exactly what we want. And so if we were writing our balanced redox reaction here, having used the half reaction method, we would probably rewrite it for clarity. So often we'll have other things that cancel out too, like water molecules or H+ and stuff. And so we'll see that in the next example. So this would be our final answer, our balanced redox reaction that we balanced using the half reaction method. Now, the other thing I wanted to mention for what's going on in these chemical reactions, we identified what was oxidized, right? We said that copper was oxidized because it goes from copper to copper 2+, and that the silver was reduced because it goes from silver ion to silver and it gains an electron. And in the previous video, I talked about some mnemonic devices to help you remember that. But I also want you to remember that this copper, that it was oxidized, the copper is what allowed the silver to be reduced. And so we also call this the reducing agent. It is the active force that allows the other chemical to be reduced. And similarly, it was the silver that pulled those electrons away from the copper. And so it was the silver that we would call the oxidizing agent. So this is just a little more vocabulary for us to keep in mind. All right, let's look at another example, and we'll go through the entire half reaction method, and I will detail all the steps. So here's our example chemical reaction. So we might receive something like manganese oxide reacting with hydrochloric acid to make manganese ion and chlorine gas. So when we look at this chemical reaction, our first step is going to be to separate it into the half reactions. So if you aren't sure what the half reactions look like, then you may need to identify all the oxidation numbers. But in this case, I hope you can see that chlorine is going to be one of the things that is definitely having its own half reaction, because we can see that here it would have an oxidation number of 0, right? It's in its pure elemental form. And over here I can see that this is chloride ion. So I know for sure that one of my half reactions is going to look like HCl going to chlorine gas. And that means that the manganese stuff is what's left. I guess I can put these closer together. So even though I don't really know for sure, because I haven't taken time to look at what's happening, I'm assuming that there must be a change in the manganese because there's no oxygen over here on this side. And that's good enough. You don't have to, if you can see how to separate your half reactions, you don't actually have to assign all the oxidation numbers before you do it. Okay, so that was our step 1. Our step 2 is going to be balancing the atoms, just like when we were balancing equations before. And here's an additional tip though. If we need extra O on either side, we're going to add whole water molecules. And if we need to balance extra hydrogens, we're just going to add H+. So let's see how that is going to look. So let's take reaction A here. We have HCl aqueous going to, that's sort of a messy looking arrow, let's fix it, chlorine gas. So when I look at these, I can see I have 2 chlorines on this side and 1 chlorine on this side. So I'm going to add 2 to this HCl, but now I have 2 hydrogens on this side and none on the other. So I'm going to add 2 H+. To balance that out. And those are always going to be aqueous. Okay, in my second reaction, I have manganese oxide, and that's going to manganese ion. So the manganese balances, but I have oxygens that I need to balance as well. So I've got oxygen on this left-hand side. I need to add water in order to balance it out. So I have 2 oxygens, that means I need 2 waters on the other side. And because I've just added 2 waters, now I have to balance the hydrogens again. So now I have 4 hydrogens, so I'm going to add them over here on the left-hand side. And water is going to be liquid phase, and H+ is going to be aqueous. Okay, we are ready for step 3. Now that we have balanced our atoms, we are ready to balance the charges. And just like we did before, we're going to add electrons. Okay, so let's take a look. Over here on the left-hand side of this, we have 0 charge. ACl is neutral. And then over here on the right-hand side, we have +2 for our total charge. So I'm going to add 2 electrons up here to balance that charge. So now we have a total charge of 0 here on the right-hand side as well. Okay, on the second equation, on the left-hand side, I have no charge on the manganese oxide, but I have 4 H+. So that would be a total charge of +4. And then over here on the right-hand side, I have 2 neutral waters +2. All right, so I need to get equal charges here. So I'm going to add 2 electrons over here to the left-hand side, because now on the left-hand side, instead of a +4 charge, I just have a +2 charge. So you don't need to make them 0 as I mentioned before. They just need to be the same on both sides. And that's totally fine. All right, so that was our step 3. Our step 4, just like we did in the previous example, is to balance the electrons between the two half reactions. Now, in the previous example, we had to multiply one of them by 2 to get the same number of electrons. But you can see here in our current example, we have 2 electrons in each reaction already, so they already balance. So we don't have to do anything else here. So we've now reached step 5, which we also did in the previous example, which is to add the half reactions together and then cancel things out if they appear on both sides. Okay, so let's look at the left-hand side. We have 2 HCl's and 2 electrons, 4 H+, and a manganese oxide. Oh my goodness, I don't know why I put a gas phase there. That would be a solid. And on the right-hand side, we have chlorine gas plus 2H plus 2 electrons plus manganese ion plus 2 waters. So we can see that we've got a few things that are going to cancel. My electrons have to cancel. I mean, they have to if I've done it right. Then I have 2 H pluses on this side and 4 on this side, so I can cancel 2 of these. And it looks like that's it. So my final form of this equation would be 2 HCl plus 2H plus manganese oxide makes chlorine gas plus manganese ion plus 2 waters. And now we're done. So let's try one more practice just to make sure that you have it, and then you'll be ready to go. We have one additional type of balancing that we do, but we'll do that in another video. All right, so let's try this example. We are given that we have this iron hydroxide ion plus manganese ion, and it makes manganese oxide and Fe2+. Okay, so why don't you pause the video and try going through those 5 steps and see if you can balance it out. All right, hopefully you did that, and what you should get for your final reaction is 2 FeOH2 plus manganese ion makes manganese oxide plus 2 iron 2 plus ions and 2 waters. So if you got that, then you are all set. You have the process down, and you can confidently balance these redox reactions. If you're not sure how to do this, then just check in with me and I'd be happy to help you out.